This code imports various libraries for data analysis and visualization, such as Math, Matplotlib, NumPy, Pandas, Seaborn, and Sklern. It also sets some initial parameters for the machine learning model, such as the proportion of data to be used for testing and cross-validation, the number of features to consider, and the initial values for the LSTM model parameters, LSTM units, dropout prob, optimizer, epochs, batch size. It then sets the seed for the random and TensorFlow libraries to ensure reproducibility of results. Finally, it sets the font size and tickle label size for the plot. Overall, this code prepares the environment for data analysis and sets some initial parameters for the model. This code is a series of functions that are used to create a LSTM, long short-term memory, network model, train it for prediction, and then evaluate its performance. The code starts with defining two functions, getMape and getXY, which are used for calculating the mean absolute percentage error and splitting the data into features and target respectively. Next is the train-pred-eval model function, which is the main function used for model creation, training, prediction, and evaluation. It takes in various parameters such as the scaled train and cross-validation data, LSTM unit size, dropout probability, optimizer, epochs, and batch size. Inside this function, the LSTM network model is created using the sequential function. This network consists of two LSTM layers, each followed by a dropout layer which randomly drops a certain percentage of its inputs during training to prevent overfitting. The output layer is a dense layer with a single unit. The network is then compiled with mean squared error as the loss function and the specified optimizer. The model is then fit to the training data for the specified number of epochs and batch size. After the model is trained, it is used for prediction on the cross-validation data. The output of the model is initially in scaled form, so it is inverse transformed using the scalar used for training. This gives the predicted values in their original scale. Similarly, the actual values of the cross-validation data are also inverse transformed. Finally, the performance of the model is evaluated by calculating the root mean square error, RMSE, and MAPE between the predicted and actual values. These metrics are then returned along with the predicted values. This code reads a CSV file from the path provided and stores it as a data frame in the variable df. It then converts the date column to a datetime type. Next, it converts all the column headings to lowercase and removes any spaces. It adds a new column called month, which represents the month of each sample. The data frame is then sorted by datetime in ascending order. Finally, the first few rows of the data frame are displayed. Overall, this code is performing data cleaning and preparation steps to make the data more organized and easier to analyze. This code sets the figure size of the plot to be 10 inches in width and 8 inches in height. Then it creates a plot using the data in the date and adj columns of the given data frame, represented by the variable df. The data is plotted with a blue solid line, and the plot includes a grid. The x-axis is labeled as date, and the y-axis is labeled as USD. This code aims to partition a given data set into different sets for the purpose of training, cross-validation, and testing. The first three lines calculate the sizes of each of the data sets and store them in three variables: numCV, numTest, and numTrain. The sizes are based on a given CV size and test size, which are multiplied by the length of the data set to get the corresponding number of rows. The remaining code prints the sizes of the datasets for the user's reference. The next four lines use slicing to extract specific rows and columns from the original dataset and store them in four new datasets: train, CV, train CV, and test. The train dataset contains the first numTrain rows and only the date and adj columns. The CV dataset contains the next numCV rows and the same columns as train. The train CV dataset contains the first numTrain plus numCV rows and the same columns as train. Finally, the test dataset contains the remaining rows and the same columns as train. The last four lines simply print the shapes of the four new datasets, giving the user an idea of how the partitioning process has been carried out. By printing the shapes, the code also serves as a way to verify the correctness of the partitioning. This code is used to convert a dataset into X-train and Y-train. The dataset is first scaled using min-max scaler to prevent information leakage. Then the dataset is split into X-train and Y-train. The shape of X-train and Y-train are printed to check if they are correct. Finally, there is a commented out code that reshapes X-train, but it is not used in this code. This code takes a dataset, CV, cross-validation, and scales it based on the minimum and maximum values obtained from the train set. This is done to ensure that the data is on the same scale as the train set, so the model can make accurate predictions. The scalar.transform function uses the scalar object to transform the dataset according to the scaling rules set during training. Next, the dataset is split into input xcv and output ycv variables using the getXY function. The n argument is used to determine the number of previous data points to use as input for each output prediction. Finally, the size of the input and output variables are printed to verify their shape and ensure they are correct. The code is used to scale the data in the train CV and test datasets. This is done using the min-max scaler function, which scales the data to be within a specified range. In this case, the range is chosen to be between 0 and 1. This is done to normalize the data and make it more suitable for training machine learning algorithms. The first step is to initialize the scalar final object with the min-max scaler function. Then, the train CV dataset is transformed using the fit transform method of the scalar final object. This method takes in the add_close column from the train CV dataset and reshapes it to a two-dimensional array. The scaled data is then stored in the train CV scaled final variable. In the next step, the minimum and maximum values of the scaled data are printed using the scalar final object. This provides an insight into how the data has been transformed and scaled. Finally, the test dataset is also scaled using the transform method of the scalar final object. This time, add_close column from the df dataset is used, and the scaled data is stored in the test scaled variable. The scalar final object uses the minimum and maximum values obtained from the train CV dataset to scale the test dataset. Overall, this code helps to normalize and scale the data in both the train CV and test datasets, making it more suitable for use in machine learning algorithms. This code creates a LSTM network model that will be used to predict future values based on input data. It first creates a sequential model, then adds a LSTM layer with a specific number of units and returns sequences. This layer also takes in an input of a specific shape. After that, a dropout layer is added with a dropout probability of 0.5. This helps avoid overfitting by randomly dropping a certain percentage of neurons during training. Another LSTM layer and dropout layer are added after that, with the same probabilities. Finally, a dense layer is added, which is the output layer with a single output unit. The model is then compiled with a loss function and an optimizer, and trained on the training data with a specific number of epochs and batch size. Overall, this code sets up and trains a LSTM network for predicting future values. The code prints a summary of the model. This code takes in a model and plots it, creating a visual representation of the model's structure. The resulting image is then saved to a file called model.png. The purpose of this code is to provide a way to visualize the model, which can aid in understanding its components and relationships. This can be particularly useful when working with complex or large models. By saving the image to a file, it can also be easily shared with others or referenced in the future. Additionally, the use of a file name allows for multiple models to be saved and compared. In this code, the model is being used to predict values for xcv, which is a set of input data. These predicted values are stored in the variable est. Next, the scalar is used to inverse transform the predicted values in order to bring them back to their original scale. The result of this operation is stored in the variable est and v. The next step involves doing the same for the actual output values, YCV. The inverse transformed values are stored in the variable YCV in V. After that, the code calculates the root mean squared error, RMSE, between the actual and predicted values. The RMSE is a measure of the differences between the predicted and actual values, and a lower RMSE means that the model is performing better. The calculated RMSE is then printed to the console. Finally, the code also calculates the mean absolute percentage error, MAPE, between the actual and predicted values. This is another measure of the accuracy of the model, and it is expressed as a percentage. The calculated MAPE is then printed to the console as well. This code is used to plot the adjusted close prices of stock over a period of time. First, the code sets the figure size to 10 by 8, meaning the plot will be 10 units wide and 8 units tall. Then, it creates a data frame called ESTDF with 3 columns, EST in V, YCV, and date. This data frame contains the investment values, cross-validation values, and dates of the validation set. The next 4 lines of code plot the adjusted close prices on the graph, with different colors and styles for each set of data: training, cross-validation, testing, and estimated values. It also adds a legend and labels the x-axis as date and the y-axis as USD. Overall, this code helps visualize and compare the performance of the estimated values with the actual values over time. This code starts by defining the variable param label as n and the variable param list as a range of numbers from 2 to 60, excluding 60. Then it creates a dictionary called error rate that has 3 keys: param label, RMSE, and MAPE PCT. The value for param label is an empty list, and the values for RMSE and MAPE PCT are also empty lists. Next, the variable tick is set to the current time using the time library. Then a for loop is used to iterate through each value in the param list range. As the loop runs, the TQDM notebook function displays a progress bar to track the progress of the loop. Within the loop, the code calls the getXY function twice to split the train scaled and train CV scaled data into 2 separate variables each: X train scaled and Y train scaled for train scaled, and X CV scaled and Y CV scaled for train CV scaled. The param variable is used as an argument in this function. Next, the train-pred-eval model function is called. This function takes in several arguments, including the X-train scaled, Y-train scaled, X-CV scaled, and Y-CV scaled variables, as well as values for LSTM units, dropout prob, optimizer, epochs, and batch size. This function trains the model, makes predictions, and evaluates the model's performance by calculating the root mean square error, RMSE, and mean absolute percentage error, MAPE. These values are then collected and added to their respective lists in the error rate dictionary. After the for loop has finished running, the error rate dictionary is converted into a pandas data frame. Then the current time is stored in the talk variable, and the total time taken to run the code is calculated by subtracting tick from talk and dividing by 60. The result is printed to the console, and the error rate data frame is displayed. In summary, this code loops through a range of numbers, splits data, trains and evaluates a model, and collects the results in a data frame. It also displays a progress bar and calculates the time it takes to run the code. This code is used to plot the root mean squared error, RMSE, and mean absolute percentage error, MEP, for a dataset. The first line sets the figure size to 10 by 8, which means the resulting plot will have a width of 10 and height of 8. The next line creates an axis object and plots the RMSE values against the number of samples n in the dataset, using blue crosses as markers and including grid lines in the plot. The following line adds another line to the plot, this time plotting the MAPE values against the number of samples, using red crosses as markers. This line uses the same axis object as before, allowing the 2 plots to be overlaid on the same figure. The next 2 lines set the labels for the x-axis and y-axis, respectively. Finally, the last line sets the label for the y-axis to be RMSE MAPE in percentage form. This code aims to find the best value for a given parameter. First, it compares the values of error rates in a data frame called error rate and returns a set of values where the RMSE value is equal to the minimum RMSE value in the data frame. Then, it assigns the value of the parameter that corresponds to this minimum RMSE value to a variable called temp. Next, the code prints the minimum RMSE and minimum MAPE, mean absolute percentage error, values to show the level of accuracy achieved. Finally, the optimum value for the parameter is printed, along with the label of the parameter and its corresponding value. Overall, this code helps in finding the best value for a given parameter in order to optimize a particular process or model. This block of code starts by defining two variables, param_label and param_list, which will be used to store the values for the first parameter that will be tested. Then, two more variables, param_to_label and param_to_list, are defined to store the values for the second parameter that will be tested. Next, there are two lines of code that split the training data into X and Y components, and then another two lines that split the cross-validation data into X and Y components. After that, the code creates a dictionary called error rate and initializes it with 4 empty lists. These lists will be used to store the different values of the parameters that are being tested, as well as the resulting error metrics for each combination of parameters. The next section of code is a for loop that iterates through the values in param_list, and for each value, it iterates through the values in param_to_list. Inside this loop, there is a function call to train, predict, and evaluate a model using the current values of the parameters. This function call also returns the resulting error metrics, which are then appended to the respective lists in the error rate dictionary. Finally, the error rate dictionary is converted into a pandas data frame, and the time taken to run the code is printed. The resulting data frame contains the error metrics for each combination of parameters that were tested, making it easier to analyze and compare the results. This code is used to plot the performance of a model against a given parameter. In the first line, the plot size is set to be 10 units wide and 8 units tall. Then, a temporary variable is set to store the error rate value for the first value of the given parameter. This is then used to plot a line on the graph with the value of the parameter on the x-axis and the root mean squared error, RMSE, on the y-axis. A legend is also added to label the line. Next, a list of colors is created to be used for the different values of the parameter. Then, a for loop is used to iterate through the remaining values of the parameter. For each value, a new temporary variable is created to store the error rate value. This is then used to plot another line on the graph with a different color and shape marker. The legend list is updated to include the new value of the parameter. The x-axis and y-axis labels are also set for the graph, and the font size is updated. Finally, the legend is placed outside the graph and the axis limits are set. This code allows for easy visualization of how the performance of the model changes with different values of the given parameter. The first line looks up the optimum values for the parameters param and param2 using a function called error rate. The function looks at the column RMSE and finds the minimum value. Then it assigns that value to a variable called temp. Next, the code uses that variable to get the value of the first element in the param_label column and assigns it to the variable epochs_opt. It does the same for batch size_opt using the param_to_label column. Next, it prints the minimum RMSE and minimum MAPE values, followed by the optimum values for param and param2. This code starts by defining two variables, param_label and param_list, which will be used to store information about the LSTM units and their corresponding dropout probabilities. Then, two more variables are defined, param_to_label and param_to_list, which will store information about the second parameter. Next, a dictionary called error rate is created, which will contain the error rates for each combination of the two parameters. A timer is started using the time_with module. Then a nested for loop is used to iterate over each value in param_list and param_to_list. Inside this loop, a function called train_pred_eval_model is called with a variety of arguments, including the current parameter values being looped over. This function will train a model, make predictions, and evaluate the performance of the model using the specified parameters. The results from this function, including the root mean squared error, RMSE, and the mean absolute percentage error, MAPE, are then stored into the error rate dictionary for the current parameter values. Once all combinations of parameters have been looped over and the error rates have been collected, the error rate dictionary is converted into a pandas data frame for easier manipulation and analysis. Finally, the timer is stopped and the minutes taken to run the code are printed. The first line of code sets the figure size to be used for the plot. In this case, the width is 10 and the height is 8. Next, the code creates a temporary variable called temp and assigns it the values from the error rate variable, where the values in the param2 label column are equal to the first value in the param2 list. This is done using a conditional statement. Then, using the temp variable, a line plot is created with the values in the param label column on the x-axis and the RMSE column on the y-axis. The style of the plot is set to be blue squares with a solid line, and there is a grid in the background. A list is created called legend list, and the first item in this list is set to be the param2 label, followed by an underscore and the first value in the param2 list. This will be used later to create a legend for the plot. A list of colors is also created to be used in the next step. Next, the code enters a for loop, which iterates through the remaining values in the more param2 list. In each iteration, a new temporary variable is created with the values from the error rate variable, where the values in the param2 label column are equal to the current value in the param2 list. Using this new temporary variable, another line plot is created with the same x-axis and y-axis as before, but with a different color and marker. This is done using the list of colors created earlier. The legend list is also updated with a new item for each iteration, following the same format as before. The x-axis and y-axis labels are set for the plot. The next line of code updates the font size for the plot. Finally, a legend is created for the plot using the list of items in the legend list, placing it on the left side of the plot and outside the figure. Overall, this code creates a line plot to compare the performance of different values in the param2 list for a given param label, with the RMSE values on the y-axis and the param label values on the x-axis. It also creates a legend to identify which line represents which value in the param2 list. This code is used to find the optimal values for two parameters, namely LSTM units and dropout prob. It first creates a temporary data frame temp by filtering the original data frame error rate for rows where the RMSE column has the lowest value. Then, it extracts the values for LSTM units and dropout from the temporary data frame and assigns them to the variables LSTM units opt and dropout prob opt respectively. Finally, the code prints out the minimum values for RMSE and MAPE PCT from the original data frame, as well as the optimum values for LSTM units and dropout prob. This code starts by initializing two variables, param label and param list. The first variable is a string that contains the label for the parameter that will be used in the model. The second variable is a list of different parameter values that will be tested in the model. Next, a dictionary called error rate is created, which will be used to store the results of the model for each parameter value. The dictionary contains three keys, with the first one being the parameter label, and the other two representing the RMSE, root mean squared error, and MAPE, mean absolute percentage error values. The tick variable is set to the current time, which will be used to measure the time taken for the model to run. The code then enters a for loop, where each value in the param list is assigned to the variable param, and the tqdm notebook function is used to track the progress of the loop. Inside the loop, the model is trained, predicted, and evaluated using the train_pred_eval_model function, which takes in the training and validation data, as well as the selected parameters. The RMSE, MAPE, and other results are then stored in the error rate dictionary. Once the loop finishes, the error rate dictionary is converted into a data frame and stored in the same variable. The talk variable is set to the current time, and the print function is used to display the time taken for the model to run in minutes. The error rate data frame is then printed, which contains the results for each parameter value. This code is used to plot the root mean squared error, RMSE, and mean absolute percentage error, MAPE, for different optimizers. First, the figure size of the plot is set to be 10 units in width and 8 units in height. Then, the error rate data is plotted on the x-axis using the optimizer column and on the y-axis using the RMSE column. The plot is shown in blue-colored X marks and is displayed on a grid. Another line is added to the same plot, which is plotted using the optimizer column on the x-axis and the MAPE PCT column on the y-axis. This line is shown in red-colored X marks, also displayed on a grid. Both of these lines are plotted on the same figure AX, which is used to display multiple lines on the same plot. The X-tick labels are set to be equal to the values present in the parameter list variable. The labels on the X-axis are set to be optimizer, and on the Y-axis, the labels are set to be RMSE MAPE point, which helps in understanding the values being plotted. Overall, this code generates a plot to easily compare the performance of different optimizers in terms of RMSE and MAPE for a given dataset. This code is used to find the optimal value for a given parameter, param and param2, by calculating the minimum root mean square error, RMSE, and minimum mean absolute percentage error, AP. The first line gets the value of the error rate with the lowest RMSE and assigns it to the variable temp. Then the value of the parameter associated with this minimum error rate is extracted and stored in the variable optimizer opt. The next three lines print out the minimum RMSE and MAPE values, as well as the optimal value for the given parameter. Consequently, this code helps to identify the best value for a parameter that would result in the lowest errors in a particular calculation or algorithm. This code creates a dictionary called D with 3 key value pairs. The keys are param, original, and after tuning, and the values are a list of parameters for a neural network model. These parameters include n, number, LSTM units, number of units in the LSTM layer, dropout prob, probability of dropout, optimizer, optimizer to be used, epochs, number of training epochs, batch size for training, RMSE, root mean squared error, and MAPE PCT, mean absolute percentage error. Next, the code creates a pandas data frame called tuned params using the dictionary D as its data. This data frame has 3 columns, one for each key in the dictionary. The values in the original column are the original parameters for the model before any tuning or optimization. The values in the after tuning column are the tuned or optimized parameters, which result in the lowest error rates for root mean squared error and mean absolute percentage error. In summary, this code creates a data frame with 3 columns containing parameters for a neural network model, including the original parameters and the tuned or optimized parameters that give the lowest error rates. This code performs various steps in order to train, predict, and evaluate a model. The first 3 lines split a dataset called train CV into 2 parts, X and Y. These are then stored in 2 separate variables, X train CV scaled and Y train CV scaled. Similarly, the next 3 lines split another dataset called test into X and Y and store them in X test scaled and Y test scaled respectively. These steps are important as they divide the data into training and testing sets, which is necessary for model evaluation. After this, the code calls a function called trainPredEvalModel. This function takes in various arguments such as the training and testing data, the model parameters, and the optimization techniques to be used. This function essentially trains a model using the X-train CV scaled and Y-train CV scaled data, and then uses this model to make predictions on the test data, X-test scaled. Finally, it evaluates the performance of the model by calculating 2 metrics, RMSE, root mean squared error, and MAPE, mean absolute percentage error. The results of these evaluations are then stored in the variables RMSE, MAPE, and EST. The next two lines of code simply print out the calculated values of RMSE and MAPE, which can then be used to assess the performance of the model. In summary, this code performs the necessary steps to train a model, make predictions, and evaluate its performance on a given dataset. The code begins by setting the size of the figure to be plotted using RC params. This ensures that the resulting graph will have a width of 10 and a height of 8. Next, a new data frame called ESTDF is created with two columns, EST and date. The EST column contains the predicted values from the model, while the date column contains the corresponding dates from the original data frame called DF. Then the code plots the training data using a blue V line on the graph and adds a grid to make it easier to read. Next, the code plots the cross-validation data using a yellow Y line and again adds a grid. Similarly, the test data is plotted using a green G line with a grid. Finally, the predicted values are plotted on the same graph using a red R' line. The legend is then added to the graph to indicate which line represents each set of data. The x-axis is labeled as date and the y-axis as USD. In summary, this code creates a graph that displays the adjusted closing prices over time for the training, cross-validation, test, and predicted data. This code first sets the figure size to width 10 and height 8. Then, it plots the adjusted close values over time for the test set only using the addJClose column in the data frame. The first plot appears in blue, and it also adds a grid to the plot for easier visualization. The same is done for the second plot, but in yellow. The third plot appears in green and is added to the previous two plots. The fourth plot, which is the predicted values, appears in red and is also added to the previous plots. The legend is set to indicate which line represents each data set. The x-axis label is set as date, and the y-axis label is set as USD. The x-axis limits are set to the dates 2018-0401 and 2018-1130, and the y-axis limits are set to values between 130 and 155. Lastly, the title is set as Zoom In to Test Set.